My name is Paul Prenny. I'm at the University of Windsor. I am a Sharcnet high-performance consultant, along with Sergey and others. And today I'm going to be talking about using pseudo-random number sequences in C++. Many of you likely have used C's random number generator at some point, the rand function, and things like that. I'm going to talk a little bit about that. I'm going to talk about random numbers in a more straightforward, easy-to-use format. If you have highly specialized needs for random numbers or anything like that, that's fine. You can ask at the end of the question, or you can submit a ticket, and we can deal with your specialized needs there. But I'm going to talk about random numbers in general, including getting more correct usage out of them, and I'm going to show you how some of these things can be used. So I'm going to talk about how to create one or more pseudo-random number generator objects, and there's distribution objects. I'm going to talk about how to properly seed pseudo-random number generators, and how you can go about that in a sane way. I want to talk a little bit about use it and show some examples. So these are all going to be using ISO C++. If you are using C, you could always call the C++ routines. If you in C++ use extr and C to export functions appropriately. And similarly, if you're using Fortran or any other languages. So if you want to use the ones that are rated in C++ from other languages, you'll have to use, give it C linkage in C++, and then you can compile and link to it like you would any C function and library. So let's just start off with using the C Standard Library. If you know C at all, you probably have used the srand function to provide a seed for your pseudo-random number generator, and the rand function to get the next seed value from it. And the reason I'm using the word pseudo, and I'm going to start dropping it, is pseudo means false. These aren't really random numbers because these are algorithms that generate numbers that we hope are random. Of course, they're generated by an algorithm, so it is not so random. But if they pass statistical tests and have certain properties that in certain ways we can consider them random, then they can be very useful. I should mention that there are applications where this is not appropriate at all. Better sources of random numbers are needed, sometimes live. So there's people who generate them based on radioactivity. You might have heard seen an article or heard some things about some internet websites using lava lamps and all these things and various other ways to get randomness. Every application is different, but if you just need some random numbers and you want, some values so you can pump them through your algorithms and things, a good starting place is to use the pseudo-random number generators. And C has one that goes back a long ways. C++, since C++ 11 has a new redesigned set of tools and libraries in there. And then there's a bunch of libraries on the internet that can be used as well. And each has their own pros and cons. So I'm going to talk about what's in ISO C and ISO C++. The ISO C Standard Library rand has a few issues that you should be aware of. So let's take a look at this program. Here's a simple program. On line 8, you see here a call to srand, and I pass the value in 5 in. You can pass in an integer that seeds the random number generator. And the idea here is every time you call rand, you get another number. So what's important to realize with these pseudo-random number generators is what is random is the sequence of numbers. And that's very important to remember. It's the sequence of numbers you get each time you call, in this case, rand, you get another number. And it's that whole sequence of numbers that's random. You don't want to start playing games with this sequence unless you you know the properties of that sequence and doing stuff, or you might lose your whatever randomness you did have. So here, srand on line 8 will initialize it with a seed value of 5. If I put a different value in there, I will get a different sequence of numbers. One nice advantage of random number generators that let you initialize them with the seed value is that you can initialize it with the same seed later and get the same sequence. And you might say, oh, I don't want that. But if you were using it for research data and you wanted to be able to recreate a run, then you would like to be able to recreate the sequence of random numbers that you also had with the original data set. So there are uses in being able to know what the seed is and to be able to somehow, in some way, in your code, record it. Now, one of the problems that people get into is they break up the sequence. If you're using C's random number generator, there is only srand internally, that seed that it initializes is like a global variable. And rand uses that global variable to get the next number. So there's a problem. You only have one random number generator in C if you're using the built-in one to the C-Standard Library. So if you have all of a sudden a point, a two-dimensional point here, I have a struct with an int x and an int y, and you wanted to generate random x and y point values, and what you did is call rand twice, and I do so on line 12. You call rand twice. What you're doing then is you're saying the first value is x, okay? The second value is y, but then the for loop continues. The third value is x, and then the fourth value is y, etc. So every second value from the sequence goes to x, and every second value offset by 1 goes to y. You've broken up the random sequence. So did you lose the properties of the randomness? This is not good. If you're intending x and y to be orthogonal, completely independent, you should be using two separate random number generators to get your values. Additionally, many people, when they use the rand function, they say, oh, I need to get the value between this number and that number. Okay, these are integers, so some low value and some high value. So what I'll do is I'll do high minus low, and then I'll use the modulus operator, the percent sign in seed with rand, because that'll give me the remainder, and that'll give me the value between 0 and the width of that interval. Is that a good way of doing it? Typically not, because you are selecting for the low order bits of your random numbers, and the random number generator numbers might not be random with the low order bits, the properties of that randomness. So you might say, well, what if I did something with that special rand underscore max variable, which is the maximum value that rand can return? Goes from 0 to that value. So what if you do something special in there and use divisions and that and manipulate the higher order bits effectively? That's better, but it's still problematic because there's all sorts of issues once you start using division. Here I have the low being 2 and the high value being 8. Rand max is typically a very large number, so it's going to work fairly well. But if my interval was closer to, the high value was closer to rand max, then you start running into little quirks and issues. So is there another way of doing it? Well, some people suggest, well, just keep calling rand until you get a value between the range you want. But if your value is, your range is fairly narrow, you're going to be doing a lot of work before you get the value. So, okay, that's not so good. So what can we do? Well, one is stop using C's rand and switch to something else, which will help. Okay, so if we're to use C++'s library, there's a header file just for random numbers called random. Okay, And every random number generator is in a class. It's an object. So this means if you have like the X and the Y coordinate thing, you can make a random number generator for the X values and a random number generator that's independent of that for the Y values. Awesome. So they're objects you can actually create independent instances of them. There's not one global thing. Okay? Nicely, each random number generator can be read from and written to a stream. So if you need to save the state of the random number generator because you want to replay it later, or you want to continue on from that point later. Let's say you're running a job. Your job now has a checkpoint. So you want to save the state of your random number generator so that when you start from that checkpoint later to run again, you reload that state and it continues on from where the sequence left off, which is awesome. Okay? In addition to the generator, the whole problem on here, on this slide, how do you map the value returned by the random number generator into the range of numbers that you would like to get and the distribution? Well, you will say it depends. What is all the math involved in all that? Do we want to become experts in all that and find out all this stuff? No, we just want something that works most of the time. So C++ defines distributions, and these distribution objects map the random number generator object values to that distribution. So a distribution could be like a normal distribution or a uniform distribution, etc. I'll talk a little bit about those later. Finally, C++ provides a nice default random engine object. If you don't care, you just want some random numbers and for a demonstration program or some use, you don't care which random number generator is used. There's a nice default one. There's also an object called random device, which I'll be talking about in a sec. And that is tied to, on most systems in your operating system, there is a random number device. A lot of hardware today includes some component capable of generating some amount of randomness as well. Random device exploits that if the implementation of the C++ standard library exploits it, and most do. Okay, so in C++, what would the code look like? Well, first thing we do is on line 1, we include random. Awesome. Okay, and then in main, this is about the simplest thing you can do. For convenience, I did using namespace standard. And what I thought I'd do is generate uniformly distributed random numbers between 1 and 100. So low is 1 and high is 100. I want 10 numbers, so I put n as 10. Okay, so how I'm going to do this is on line 9, I declare a random device. You should only use this to seed your random number generators. Do not generate zillions of random numbers with it. The random number device has a limited amount of entropy, and on many systems, once that's consumed, it will wait until there's more entropy. So I won't go into the details, but you only really want to use random device to seed your random number generators. On line 10, I declare a distribution. There's all kinds of distributions. Here I'm using a uniform integer distribution. And the uniform distribution will always go between a low value and a high value. So I pass in low and high to the constructor, and the variable is called dist. Okay, and on line 11, I chose a Mersenne twister, commonly used random number generator, MT19937. You might be familiar with if you've used random number generators before. It's often what it's called. And very importantly, this is an object that generates random numbers, okay? But I need to pass it a seed. Now in C++, all of the random number generators can be passed a seed that's basically a 32-bit integer from random device, but it can be any integer that you pass it. And that will initialize the random number generator. Of course, that seed is only 32 bits, many of the random number generators, this is not an issue. But with Mersenne twisters, which is why I'm using it here, it is an issue. Mersenne twisters have hundreds of bits of seed value that you'd ideally like to set randomly. So you just don't want to use a 32-bit number. The C++ standard does actually dictate an algorithm that if you give it a 32-bit number, what the algorithm does to seed the rest. But I'm going to show you how to seed the entire Mersenne twister. On the other hand, if you're using one of the other random number generators in C++, in the vast majority of cases, you can just seed it with a value from random device. Now, I'll mention one thing here. You should realize the random device, the random number generator, okay, and the distribution, yes, you declare them on lines 9, 10, and 11. They're declared there. But when you use them, they appear like they're function calls. So on line 11, you can see I'm using the random device with RD open round bracket, close round bracket. It looks like a function call. That's because all of these are function objects. And so if you're wondering why the round brackets after RD, it's because it's a function object. So after it's declared as a variable, if you use it with round brackets, you're actually getting a new random value. Okay, if you're new to C++, it's done with function call overloading. The line 14, you can see dist appears and open round bracket, generator, close round bracket. So it looks like a function call. At that point, the dist object, what is it doing? Well, the function call with it is it's passing in the generator. So the generator always gets passed into distribution. So you don't need to make 29 distributions. If you only need one integer distribution, but you have 10 generators, you only need to declare one distribution object if they all go from 1 to 100. Because the distribution object does not store the random number generator in it. Instead, when you call the function call operator of distribution, you pass in the generator. And that's what you see on line 14. And that will generate the random number for you, properly mapped into the distribution you're using. So the distribution here is a uniform distribution, so it's going to be mapped properly from whatever the random values are generated from in the generator into values from 1 to 100. So that's fine. Mersenne twisters, though, if you're using the 32-bit, which is the MT199371, or the 64-bit one, MT19937_64 in C++, the Mersenne twisters have hundreds of seed state bits that you want to initialize. So the question is, how do I initialize them properly? So I have them here in the slides, so you can see how to do it. It is very straightforward, but then you want to wrap it up and throw it into a function, which I show you how to do, and then the code looks clean again. So we want the random device. We'll need to declare a vector to hold the type of objects required for all these seeds, and then we need to generate those n seed values, which is on line 15. You see the state size. That's the number of seed values we need to generate each time we call a random device, which is the RD. Okay, so we put all that into a vector, so basically an array. We have to use this seed sequence object on line 20, passing in the vector. That gets initialized, and then we pass the seed sequence object to our random number generator. So that's a lot of steps, and it's very annoying. Nobody wants to do that in their code. So it is much easier to put this in a header file. This does, and I called it make Mersenne twister. And all it does is it returns back the random number generator randomly seeded. Okay? A lot of people will say, well, I like to seed it with the clock. The problem is a lot of the clocks people seed things with, the clock only changes every second. Okay, it depends which clock algorithm you're using or call you're using, but a lot of them will only change every second. You know, in today's computers, you know, the likelihood of, if you have a bunch of random number generators, one after another in your code, of all of them being within a few nano, microseconds, you know, max of each other is very high. So in other words, they'll all be initialized in 1 second and they'll all have the same seed, which is probably not what you want. It's much better to ensure you get some random value in them. Okay, so if you put your function to generate the random number generator, whatever one it is, you can make a function for each if you want. Put it in a header file, happiness, you don't have to look at that code again. And then you can go back to having same code here, where you can just say, I want a low number, I want a high number. Okay, so here I have floating point numbers, double, 1.1 to 100.1 instead. Okay, and I just call make for send twister, and that gives me back my generator. Awesome. Randomly seeded, even better. Okay, so I got my distribution from low to high, and then I just want to output a bunch of values. So that's pretty good. Okay, that's what you want to do. And the Mersenne twisters are very common. So I showed you that case. Virtually all other cases, you can just seed it with the return value of one call to the random device generator to get that. Where you can get some more information on random number generators, and I'm going to, and some libraries, and I'm then going to show you some examples. So if you go to Wikipedia's page, it's not a half bad place to start. Of course, you can go to research papers and all that too, but if you go to Wikipedia's page first, you can get a sort of a general overview about pseudo-random number generators and find out, you know, some things about it without it being overly technical. And when it does, you can skip over it, but you can get an appreciation of what's involved and take that into account for whatever your use cases are for your research. Now, what I want to point out on this page is if we scroll down to the, I think the See Also section, they have a nice link here, a list of pseudo-random number generators. Okay, if you click that link, it will take you to this page. And what's really nice about this page is it shows you this table of various random number generator methods. So these are random numbers, pseudo-random numbers being generated by an algorithm, various methods over the years, and mentioning the year and the persons involved, and links to additional pages on it and some comments on it. And this is very useful because if you do have specialized needs for your random numbers, you might want to take into account looking at this list. If you can generate them from an algorithm. If you can't, you need an actual table and other things, then you're doing something different. That's okay. Every research problem is different in terms of their needs. For cryptography, you definitely will want to look at these and choose the appropriate hash functions and ciphers and generators for them. I should mention the C++ code examples I've given. If you're using C++ 98 and you can't use C++ 11 or newer, the random number generators in C++ came from the Boost project. So if you go to boost.org and you look at the documentation for random numbers, it'll take you to here, boost.random, and this tells you how to use them. There are additional things in here that are not in the standard, but this is where you can get support for C++ 98 using random numbers, or if you're using some of the ones that aren't in C++ in Boost, this is perfectly fine to use. Okay, and it's very similar to the C++ one. Finally, I want to mention, if you are programming in C++, where can you get more information without reading the very dry standard document for C++? You can go to this website, cppreference.com. You can click on headers, okay? And if you click on headers and then you choose random, it'll give you this page. And this page nicely summarizes what's in the random header. And you'll see that there's random number engines. There's a variety of them. There's the linear congruential engines, the Mersenne twister engines, and the subtractive carry engine. So these are three general categories, different ways of generating random numbers. Just point out to you the congruential engine. The way these are defined is in terms of A, C, and M. These are the constants for those of you who know how the linear congruential engines work. So that means if you have, for example, numerical recipes in C's values for A, C, and M, you can declare this as a type. You know, just like here, there's a declaration right here for this min standard underscore rand 0 in the C++ standard. It's using these values for A, C, and M. So you can substitute your own values in there for the linear congruential engine. You can do similar things with the other engines that are available. The other thing I want to point out to you is there are a number of, I've only talked about the Mersenne, which is the MT19937 generator, but there are a number of other generators available, and you can see the constants and everything that are defined. The standard shows things that are studied random number generators, so people will know their properties. Okay, and you can see now here that there are a variety of distributions. The most common many choose for many applications are the uniform ones, so evenly spaced values over the integers or over floating point numbers, the reals. There are Bernoulli style distributions. Okay, there are Poisson style distributions. There are normal distributions, distributions for sampling purposes, and in particular, this is really handy because you might say, oh, between these two values, the probability is something, and then between another two values, the probability is something else, and you want to generate random numbers taking into account the different probabilities of different pieces of your distribution. That is what these are for. Okay, and there's seed sequence. Also on the site, there are example code blocks and things like that that show you how to declare them, or on other pages how to actually use them. Finally, I want to show you some examples. Okay, so if we have some code, let's look at a uniform distribution first. Okay, so I have some code, a value for low, high, and an n. Okay, the main thing is I declare my distribution. I'm doing double, so I should choose real here. I'll put my low and high values. Okay, and then I'm going to for loop through them and get those values. So let's just see what this does. There we go. And each time I run it, I get different values. Awesome. Okay. So then you might say, okay, so I need to checkpoint. Okay, and if you need to checkpoint something, you need to save the state because the program's going to be shut down, and then you're going to restart it later, but you're going to reload all your data, and you want to reload your random number state so you can continue on from where you left off. Okay, well, we can do that. Now, to fake it, rather than make a file, I used a string stream in C++, but this could be any file object. Right here, I called it fake file. So it's low, high, n. I have some uniform distribution, whatever, doesn't matter. But the main thing is I have some random number generator. Okay, so whatever one I chose to use, I got it in this variable. Awesome. Okay, so what I'm going to do is I'm going to save my state of my random number generator, which I do right here. All you have to do is take your file object, use the bit shift left operator, and your random number generator. So you might say, could I actually do that with cout? Yes, you might not like the output, but you could put cout random num generator right there. That would work. Okay, and that will save the state. The reason for the if statement is, of course, when you write something out, the stream can fail, and that means you didn't really save the state, so it's good to know that. I can use the random number generator, blah, 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 but let's just say I want to reload the state now, so I can replay it, and then I can use the random number generator again. Okay, so that's what this program does. And when I reload it, I just do it the other way, just like you're using CN or reading from an input file. You use the right shift, bit shift operator. So if I run that, you can see that I save the state, I generate some numbers, then I reload the state, and I wind up generating the same numbers. If I comment out the reloading of the state, I will get the next numbers after this last one it generated. So that allowed me to save and reload the state. So it's very, very straightforward to do, but very handy, especially if you're checkpointing or have some reason to save it. Maybe you want to save the state before you generate any numbers. So for research reasons, if someone asks 5 years later, well, what was the sequence of numbers you used? You could regenerate them. And should mention the C++ standard mandates in the standard the values that the random number generates, the constants and stuff involved. So even if you switch from computer to computer to computer, your values should be the same for all your random number stuff if you're using ISO C++ compliant implementation. Okay, so there's other random number generators, okay, and distribution. So really the generators are less interesting. You choose a generator that's appropriate. And then it's really the distributions you want to play around with. So if we were to look at the Bernoulli distribution, okay, so here we go. Okay, now with a Bernoulli distribution, what you do is you generate your, whatever your random number generator, you create an object for it, okay? And then for your distribution, you pass in the probability. You know, in the case of Bernoulli, it's only true or false, so you pass in the probability, and the probability here, I set to 0.25. So now, that probability, this random number generator is the same. I just put bool alpha here so we can see true and false instead. If we run this, and we generate 10 values, we can see that we got true twice, and the other 8 values are false. We run it again. This time we got, looks like 1, 2, 3, 4, 1, 2, 3, 4 values that are true. Okay, and this time 1 value that's true, etc. So this is a Bernoulli distribution, and the probability of 0.25 is the probability we're going to get true over the sequence of numbers as we keep generating them on and on. Okay, some of you might say, what about a normal distribution? Okay, a normal distribution, you pass in the mean and the standard deviation you want. The rest of the code is the same. Of course, you're using normal distribution with, say, a double, but the rest of the code outside of this line is basically the same. So if we were to see the normal distribution, there we go, and we can get values for them. Okay. Kind of interesting. Now, there are Weibels, there are Gamma, there are things like this. I'll show you on the website where you can, how you can figure out, oh, what do I pass it? Although in most cases you can guess what the values are, but better than guessing, you can look them up on the website. But let's take a look at this piecewise constant distribution first. Okay. So we have a piecewise constant distribution. So what we'd like to do is this n is still the number of values we're going to generate. And what we'd like to do is define this sequence of intervals. So how about going from 0 to 1, 1 to 100, 100 to 150. So overall, we're going from 0 to 150. Okay? We can define this using a vector, and all we have to do is put the boundary areas. So it's kind of nice. 0 to 1, 1 to 100, 100 to 150. Awesome. Okay? And then what we need to do is to define the probability of generating a number in each interval. Now, nicely, the standard lets you provide weights, so you don't have to normalize the probabilities. You can just use numbers, and the distribution will take care of normalizing those numbers for you, so they'll convert them into probability. So the weights we'll use, if it's between 0 and 1, we'll use a weight of 2. If it's between 1 and 100, we use a weight of 0. In other words, we don't want any numbers between 1 and 100. And the weight between 100 and 150 is 1. So the values between 0 and 1 should be twice as likely as the values between 100 and 150. And we don't want to see anything between 1 and 100. Okay, so we put piecewise constant distribution. Okay, we're using doubles here. We have to say what the beginning and the end of our intervals are. So that's what we did there. And we got to give the beginning of our weights. The weights sequence has to be the right length. So if you have a total of 3 intervals, you need 3 weights. That's an implicit assumption. That's why you don't pass in the end of the weight. So anyways, once you do that, magic, this for loop hasn't changed the whole talk. It's still dist with the random number generator, but this time dist is this piecewise distribution. So let's just see this run, piecewise constant distribution. So there we go. So these aren't sorted, but we got a bunch of values between 0 and 1, okay, and we got values between 100 and 150. And if you keep running it, you'll see that's the case. Wonderful. You might say, okay, well, what about this linear one? Okay, same deal here. We have an interval sequence, and again, we just put the boundaries, so 0 to 10, 10 to 100, 100 to 150. Okay, now what we want to do with the linear interval is the weight sequence, we got 4 this time, okay, and I put comments in the code because it's easy to forget. What we want to do is increase the probability from over the interval of 0 to 10. We want to use the same probability over 10 to 100, decrease the probability from 100 to 150, and at half the rate of increase for 0 to 10 for the last one. Okay, how can we do this? Well, we basically want to go 0 to 2, we want to stay the same, and then we want to go 2 to 1. So we're again using weights. The distribution will normalize into a probability. This is identical to before, except it's linear, not constant. So it'll linearly increase here. It will stay the same in this interval, and it will decrease here. Okay, and again, this will work. And we want linear distribution. And nicely, it gives that. And so there are a whole bunch of distributions here. Obviously, I have a bunch of examples here. Using them would all be similar. The more complicated ones were the ones I just showed you. And you might say, okay, well, how do you figure out heads or tails with those distributions? Well, on this random page, so cppreference.com, click header, and you choose random header, okay, and then here we got our distributions. So if you want to know, oh, how do I use a normal distribution? Let's start with that one. Open that. Oh, I'll just click the link here. Okay, and it will tell you normal distribution will give you the probability function. Okay, that's nice. Okay, it'll tell you a bunch of stuff. And the way this site is organized, the constructors are always their own link. So what you have to do is click on constructor to see what the constructor arguments are. And then it tells you. So you can default initialize it, in which case it'll use the effective 0 seed, whatever that means for that distribution. Or you can pass in A and B, the low and the high. Oops, I clicked the numeric limit there. Or you can construct it this way. So that's how you construct your uniform distribution. And there's information on it. Uniform is pretty straightforward. At the bottom here, they do give code examples. So you can try those out. You might say you're more interested in Bernoulli or binomial or something. Okay, fine. You click on Bernoulli, And you can see the Bernoulli distribution. Okay, there's probability stuff. But if you click constructor, okay, you'll see that the constructor takes a probability. And you can see the 2 here, right here it says 2, uses P as distribution parameter, which is just a fancy way of saying the probability P. And of course that matches the definition given here. Okay, if you're interested in Poisson, the same thing. The normal distribution, if you go down and then you click constructor, you'll see the mean and the standard deviation. Some of these have multiple constructors, so it is worthwhile looking. Chi-square, etc. Sampling distributions, let's just take a look at the constant distribution. Okay, the definition here is a little more complicated because you're talking about weighted intervals. The constructor, talks about using iterators and all that, which is one reason why I showed the example. Most people want to see an example, but it explains each constructor that you can use. And of course, they do give an example down here, so that's handy as well.